All right, we're making progress through this calculator section of the 2004 released exam. Let's start with number 88. The graph of a differentiable function is shown above. So that's the original function f. Let h be a new function. And h is defined as the integral of what we're looking at. Which of the following correctly orders things? So the function, this would be the integral of 0 to 2 on what we're looking at. Well, that's just the area. Okay, they want us to put them in order, by the way, from biggest to smallest. So I'm seeing that this one's actually a pretty big positive, right? That's all above the x-axis. So let's keep going. I see that the function f crosses through the x-axis there and changes to be negative. So the derivative of an integral is just the function. Okay, so let me write that down. H of 2 is actually just what we're looking at here. H prime, I think I said it wrong, H prime of 2 would just be the derivative of an integral with x plugged in, so that would be f of x. So this would be 0. And that's because I'm looking at the point 2, 0. I'm just looking at it. I'm just reading it off the graph. I'm not looking at slopes at all. I'm just reading it off the graph. And then they want us to talk about second derivative. Now the second derivative would be the derivative on what we're looking at. So the second derivative would be slopes. So as I'm looking here, I see that the slope is negative. That's all I need to know to put these in order, folks. H of 2 is definitely the biggest. H prime is in the middle. And then H double prime is the smallest. And that was option E here on the answer set. Right, so all you had to do was analyze positive and negative. Of course, the fact that the derivative of an integral is just the function was part of the test here. And I think just reading that point off the graph might be tricky for students also to recognize that what they're looking at is actually h prime. So they just read it off the graph what f prime would be. All right, moving on. 89. What is the area enclosed by these three things? All right, so if you go to the calculator and we're going to do that here in a second. E to the x, of course, minus 2 would be down here, and it would be going up like that. That would be e to the x minus 2. And then the sine function is going to start here and go up, and it's going to hit at some point. You could, take time to reason it out, but where it might hit. But we're going to use the calculator to do that, of course. And then x equals 0. X equals 0 is just a vertical line right there. So we need to figure out this value right here. I'm going to call it a. So we need to integrate from 0 to a on the upper minus the lower, right? I'm sure your teacher drilled that into you. So the upper function here clearly is sine x minus the lower function. And because it's e to the x minus 2, you have to put it in parentheses when you put that in the calculator. Otherwise, you very well could get this wrong. dx. All right, so there's the integral we need to plug in. All right, so we will need to figure out where they hit. We could try to do that algebraically, but I think in the end it's going to be faster to just do this with a calculator. So there's my calculator. I'm going to go to y equals, and I'm going to type in e to the x minus 2 for my y1. And then, and by the way, I'm going to show you a really cool trick that maybe some teachers don't show their students. So make sure you're paying close attention to what I do here. I'm going to show you two different tricks. All right, so if we go to graph this, I might need to reset my window because it's left over from before. All right, so let me go to window. Well, actually, we're okay. We're okay. So you can see it hits right here. So that's the value that we're going to need to find. There's that vertical line that I talked about. So we're going to be integrating from here to a, whatever the heck a is. And don't assume it's 1, because I don't think it is. So we do second trace, that gets to calculate. You go down to intersect, and it says, okay, tell me what the two functions are. 1, 2, and then you got to navigate, somewhat close to the where it hits, hit enter, and there it is. The intersection is this number right here. Now, I'm not going to write that down. I guess I could, but just 'cause I don't like, especially on when you get to the free response, you do not want to be using rounded numbers to do any other calculation. So right now, x equals this. So here's the first little trick I'm going to show you with the TI. Currently, the variable x now holds that number. So if I type x, it's that. But I could lose that. Like if I trace somewhere else on the graph, I'm going to lose that. So watch what I do. I'm going to store it. So what you do is you take the value and you hit that STO button with the arrow. I like to think about it like you're shooting the number into, I'm going to store it in A. So now let me hit enter and it says, okay, yeah, I did that. So watch, now whenever I type A, it has that number stored. Now I'm going to just use A when I type it in. Watch. I'm now going to go to Math, Integration, which is number 9. My bounds are going to be 0 to A. All right, here's the second trick. So the first trick, you guys probably knew how to store variables. Rather than typing sin x, do you remember that was my y2, wasn't it? So you can click the vars button, vars, V-A-R-S, go over here to the y variables, select function, and select y2. Boom. So that's actually sin x minus, I'm going to do y1. So I'm going to go back to vars. I'm going to click to the right to get to my y variables. My function is y1. So that's the upper minus the lower. Upper minus the lower. And I'm going to put an x here because that's my variable. So I didn't have to retype things. I think that's probably quicker than retyping, and time is of the essence, as you know. So let me hit enter, and I get 0.745, and that is C. And I'm looking at the key, 89. C is the right answer. What do you know? We did it. All right, moving on to number 90. A particle moves along a line so that its velocity is given by this. Now, this is a cubic, and with also, oh my goodness, with an exponential at the end. So some crazy stuff is going on here. This thing could be positive or negative. Do I care what it looks like? Not yet. I'm not sure that I'm going to need to know what it looks like, but let's see. For what values of t is the speed of the particle increasing? Okay, so speed is the absolute value of this function right here. So when is it increasing? So that would be slopes are positive on the absolute value when we're moving away from the x-axis on the absolute value function. So I think I do actually want to graph this. So let's go back to y equals. I'm going to clear out these two. When typing this in, don't forget to use your absolute value. So we're going to do the absolute value of the given function. Now take your time plugging this in, minus x to the third. Real easy to make a mistake on your data entry. Plus 2x plus 2 raised to the. So up in the exponent is your variable like that. Now make sure you got that absolute value. All right, double check, look at it again just to make sure you typed it in right. And I messed something up, didn't I? I forgot the square, so I'm glad I looked at that. Second insert, I am going to square that. There it is. Plus 2 to the negative x. And now I hit my graph button, and let's look and see what this graph looks like. All right, it's coming down, of course. Oh, then it goes back up, then it comes down, and then it goes up again. Now remember, this is velocity, and we want to know when is the speed increasing? When is the speed increasing? So speed would mean, I'm sorry, when is this increasing? It means when you have positive slopes. When is it moving away from the x-axis? So this is from here to here, it's moving away. But then the speed actually goes down for a bit, and then boom, something happens here, and the speed starts going up again. All right, so the answer is whatever this number is to here, union from here and beyond. So you can look at this and pretty well know the answer, right? Because this is 1, this is 2. So it's got to be this one down here. Here's my 2 to infinity. And then these numbers right here, if you were to trace this function, I'll show you. If you trace this, there's your 1.7 or 0.17, this number right here to start out with. And then it does peak at 1.2. So you can be pretty confident without doing a whole bunch of wasting of time that option E is the correct answer, and that is the correct answer. All right, moving on. I think we have a couple more here. Let f be a function defined by all these tables. So I can't quite get them all on the screen for you, but we'll be able to find the answer easy enough. Let f be a function defined such that it's always increasing. This means f is increasing all the time. That's what you need to write down. And it's concave up. What does that mean? That means it's accelerating. So this is concave up. So I'm starting to think like an exponential or something. You see how I reasoned all that out with just those 2 bits of information. So going through, which of these appears to be accelerating up? This one goes down by 1, down by 2. Oh, that's accelerating in the wrong direction, actually. So it's not A. This one, as these go up by 1 every time, these are accelerating, so B is a possible answer. Let's check the others just in case. These are just going up by 3 every time. That's linear. That's not the answer. Letter D, this goes up by 8, then only by, what are we going up? 6, and then up by 2. Well, that's actually decelerating. That was actually concave down, I think. And then this one is down 1 and then up. This is all over the place. So that's not it either. So the only one that it could be is letter B, and that is the right answer. All right, number 92. 92. I think this might be the last one, and it is. So here we go. You ready? This is a good one. I like this one when I previewed this one earlier. A table gives values of the differentiable function. Let me get rid of my calculator here. I don't know that we're going to need it anymore. It might be a distraction. Functions f and g are above, and also, of course, the derivative just on f. But we don't have a g prime column. We don't have a g prime column. G, as it turns out, is the inverse of f. So what is the value? What is the slope of the tangent line at 4 on G? So back in pre-calculus, you learned that if this point is on, okay, if f of A is B, right, then over here, on the inverse, a B is going to turn back into an A. So let me give you some numbers to make this more real. So if this were 5 and this were 1, then this would be a 1 and this would be a 5. So on f of 5 turns into a 1. On the inverse, then a 1 turns back into a 5. Do you remember what's true about the slopes? So let's say this is f. What does the inverse look like? The inverse is symmetric across a 45. So if the slope here, I'm just going to make up numbers, okay? So if the slope here is up 2 over 3, then over here it's going to be reversed. It's going to be up 3 over 2. It's the reciprocal. So we're going to need all that information in this problem. They want us to figure out g prime at 4. So I go down here to 4, and I see on g, 4 turns into -2. That's on g. Now remember, g is the inverse. So the sister point would be up here, where a 2 turns into a -7. You with me? And then the slope there is up 4 over 1. So therefore, the slope on the inverse of function would be what? The reciprocal. It's 1/4. It's 1/4. The answer there is 1/4. So that was a lot of processing and really understanding what goes on graphically in these values. It's a pretty neat question. I remember trying to write these questions to give tests to my students, and it was always a challenge to write them. So this is a pretty cool one. All right, so hopefully this series with the calculator section has been helpful. I will definitely do the free response problems on this 2014 exam also, and I'll include that on the playlist. All right, good luck in all your studies.